So here we have a gas law problem that also involves a little bit of fluids. It's a cylindrical diving bell, and we're given the diameter of the diving bell is 4 meters, which means the radius is 2 meters. So what I've already calculated here is the area of the top of the diving bell, which is this shaded area up here. So of course the equation for area is pi r squared. So plugging in a radius of 2, 2 squared times pi gives an area of 12.5664 meters squared. And the volume of a cylinder, I already have that calculated here, is you take the area, which we've already calculated, and you multiply by the height of the cylinder, which we know to be 5 meters. That's given right here in the problem. So the total volume of this cylinder is 62.8319 cubic meters. And the first question wants us to find the number of moles of gas, nitrogen gas, although it doesn't matter what the identity of the gas is. We're finding the number of moles of gas that is contained in the diving bell before the diving bell is placed into the ocean. That comes later when the diving bell goes into the ocean. All right, so solving number 1, the solution is simply in PV equals nRT. So P is pressure, V is volume, N is moles, R is gas constant, and there are 2 versions of the gas constant, and T is temperature, which always has to be in Kelvin. For this problem, the R that I'm going to use is 8.31 cubic meter Pascal over mole Kelvin. So when you're using this gas constant, the volume has to be cubic meters, the pressure has to be pascals, and whenever you're doing a gas law problem, the temperature must be Kelvin. All right, so all we do is we rearrange the ideal gas law here for moles. So N is equal to PV over RT. We know that the pressure, if the diving bell is sitting here at sea level, we know the pressure at sea level is 1 atmosphere, and 1 atmosphere is equivalent to 101,300 pascals. So that's the pressure on the diving bell, on the gas in the diving bell before it goes into the water, because it's open to the atmosphere. So the pressure is 101,300 pascals. I'm using pascals because that's what the gas constant calls for. The volume we've calculated, it's 62.8319 cubic meters. The gas constant is 8.31 cubic meter Pascal over mole Kelvin. And the temperature is 25 degrees Celsius. Now the way you convert Celsius into Kelvin is by adding 273. So 25 degrees Celsius is equivalent to 298 Kelvin. So the kelvins cancel out, cubic meter cancels out, pascals cancel out, and we're left with mole, which is in the denominator of the denominator, which is the same as the numerator. And this gives us an answer of 2,570.2 moles. And that's the answer to the first question. Now the second question, this is just this should have said number 1. The second question is just a chemistry conversion. The number of molecules of nitrogen gas that are in the diving bell. So 1 mole of anything, 1 mole is equivalent to 6.022 times 10 to the 23rd molecules. Or anything for that matter. It could be a mole of donuts. 1 mole of donuts would be 6.022 times 10 to the 23rd donuts. So this is our conversion we're going to use. So you set it up like this. 2,570.2 moles of gas. In this case, it's N2 gas. Or we'll just say moles of N2. So the conversion is 1 mole of N2 is 6.022 times 10 to the 23rd molecules of N2. So the moles cancel, and we get 1.55 times 10 to the 27th molecules. Okay, the third question is also a basic chemistry conversion. So we're given in the problem the molar mass of N2. Now you can always find the molar mass on the periodic table. If you look on the periodic table under nitrogen, it'll say 14.0. The unit's not given on the periodic table, but the 14.0, the unit for that is grams per mole, meaning the mass of 1 mole of nitrogen gas is 14.0 grams. But nitrogen gas exists in nature as N2, so the molar mass for N2 is going to be double that, 28 grams per mole. So that's going to be our conversion. So we know that we have 2,570.2 moles of N2. So you set this up, so moles cancel. 1 mole of N2 has a mass of 28 grams. So moles cancel out, and this gives us an answer of 71,966 grams of N2, which in kilograms would be 71.97, we'll say. 71.97 kilograms. Or you could just leave it in grams. Okay, so that's the first 3 questions. Now on to the fourth question, which is the trickiest part. All right, so now the diving bell is submerged 300 meters below the surface of the ocean. And I drew in here, this represents the surface of the ocean up here. So the diving bell starts out of the water and then is submerged 300 meters deep. So let's get that on here. 300 meters below the surface of the ocean. And what we're asked to find is how high into the diving bell does the water rise? So what's going to happen here is the water level inside the diving bell, so this represents the water level. The water is going to compress the air inside the diving bell and make the volume smaller. So we have a starting volume up here, which we already calculated, 62.8 cubic meters, and then there's going to be an ending volume that's smaller. So this is a problem where we have a gas, the gas is the air. We have a gas that is under 2 different conditions. Or I should say the gas is nitrogen, because the problem says it's nitrogen. All right, so we have condition 1. So I'm going to label this V1, T1, P1, and then down here we have condition 2. So this is V2, T2, P2. All right, so we need to find the equation that fits this problem. So the way you do this is you start out by writing PV equals nRT, and you go through and identify the variables that remain constant. So starting with pressure, the pressure does not remain constant because as you go deeper and deeper in the ocean, the pressure gets greater, which you know if you've ever swam in a deep pool. If you swam down to the bottom of a deep pool, you feel that the pressure increases. So pressure does not remain constant. The volume of the gas inside the cylinder does not remain constant. Up here, the volume is the whole thing. It's the volume of the whole cylinder. And then down here, the volume of the gas is much smaller. And the rest of this is water. The water comes in. Okay, so volume's not constant. Moles is constant because gas is not being added to the cylinder, nor is gas leaving the cylinder. So moles remains constant, and the gas constant is always constant. And then lastly, temperature is not constant. Up here it's 25 degrees Celsius. Deep in the ocean it is 8 degrees Celsius. All right, so what we do is everything circled goes to one side, everything not circled goes to the other. So we get PV over T equal to NR. So if NR is constant and it's equal to PV over T, that means that PV over T must also be constant. So the equation we're going to get is P1V1 over T1 is equal to P2V2 over T2. So basically what we're saying is the ratio of PV over T is a constant because it's equal to NR, and NR is constant. So this is our equation that we're going to be working with for this problem. All right, before we go any further, we need to figure out P2. Now this goes back to our study of fluids. To find the pressure at a given depth under the surface of a fluid, the equation is you take the pressure of the atmosphere, which is the starting pressure before going underneath the surface of the fluid, and you add dGH. So this was discussed back when we did fluids. So this is how we're going to find what P2 is. All right, so P2, so the pressure of the atmosphere, you want this to be in pascals, 101,300 pascals. That's what the pressure was up here before the diving bell was submerged. Plus, all right, the density of the water is given right here, 1,025 kilograms per cubic meter. Gravity is 9.8. And H is the depth, which is 300 meters. So this gives us the pressure 300 meters underneath the surface of the water, and that comes out to be 3,114,800 pascals, which I'm going to convert into atmospheres. The way you convert that to atmospheres is by dividing by 101,300 pascals, because one atmosphere is equivalent to 101,300 pascals. So in atmospheres, that is 30.7483 atmospheres. Okay, so now what we're going to do is we're going to solve for V2. So we're back over to here now. We take this equation. V2 is going to be P1 V1 T2 over T1 P2. Okay, so plugging our values here. P1 is 1 atmosphere. V1 is 62.8319 cubic meters. T2 is, you want to be in Kelvin here, 281 Kelvin. T1 is 298 Kelvin. And then P2, we just solve for it, is 30.7483 atmospheres. So I'll just point out here, it really doesn't matter what our pressure unit is as long as they're the same. But it does matter what our temperature unit is. Temperature always has to be in Kelvin. All right, so atmospheres cancel, Kelvin cancels, and we get V2 equal to 1.9269 cubic meters. So that is the volume of the gas here. So it used to be a volume of 62.8 cubic meters, but the water has compressed the gas inside the cylinder, so now the volume is much smaller. And the reason for that is the pressure 300 meters underneath the surface of the ocean is pretty significant. So the gas has been compressed by the pressure of the water. All right, so the next thing we're going to calculate is, clean this up right here. So we are now going to calculate what this height is right here. So I'm gonna put this down as a capital H. Okay, so the gas has been compressed. The volume of this gas in there is going to be equal to A, where A is the area of the top of the cylinder, multiplied by H, which is the vertical distance to the level of the water. The volume of the gas is going to be A times H. So using that equation, V equals A times H. So H is V over A. We know the volume of that gas is 1.9269. And the area of the top of the cylinder is, we have it up here, 12.5664 meters squared. So we now know that this vertical distance to where the water level is, from the top of the cylinder to where the water is, that comes out as 0.153 meters. So the full height of the cylinder is 5 meters. So the question that we're looking for is how high does the seawater rise in the Bell when it's submerged to this point? So we're basically looking for X. X is going to be 5 meters. 5 meters is the full height of the diving bell. We take the 5 meters and subtract away H, and X comes out to be 4.85 meters. So it's 5 meters minus the 0.15. The water level inside the diving bell comes up almost all the way to the top, 4.85 meters.